looks like we are live. Let's continue. Let me open the table of content first. Okay, we are on chapter 18, paging introduction, and still on section homework simulation here. Let me open that. Okay, we are in this section. Basically, we are checking out this Python script, paging linear translate, to see how the what is it called, virtual to physical address translation works with linear page table. We already take a look at question 1, question 2, and now we are in the question 3. To be precise, we are trying out this configuration, maybe something like that. Basically, we are checking out what is it called? What happened when we use 20%? What happened when the address space is 20% use? Something like that. This is the percentage usage of the address space. Okay, and also I have a few questions about the simulation. We already answered some of it, and now let's take a look at this one, the exclusive OR. Okay, let me copy this in the chat in case anyone wants to take a look too. Exclusive OR, exclusive disjunction. Oh, okay. Exclusive alternation, logical non-equivalence, or logical inequality. Oh, logical inequality is a logical operator that compares to truth value, or more generally to formulas, such that it gives the value true if both arguments have the same truth value, and false if they are different. Oh, this is the logical equality, and this is the logical inequality. Okay, whose negation is the logical biconditional. In logic and mathematics, the logical biconditional, also known as material biconditional or equivalence, or bidirectional implication, or bi-implication, or bi-entailment, or exclusive NOR, is the logical connective used to conjoin two statements P and Q to form. Let me check. Biconditional, okay. P and Q to form the statement P if and only if Q, where P is known as the antecedent. An antecedent is the first half of the hypothetical proposition. Whenever the if clause precedes the then clause, in some context the antecedent is called the protasis. Okay. With two input, XOR is true if and only if the input differ. One is true and one is false. With multiple input, XOR is true if and only if the number of true input is odd. Okay, it gets the name exclusive OR because the meaning of OR is ambiguous when both operands are true. When both operands are true. XOR exclude that case. Some informal ways of describing XOR are one or the other but not both. Oh, either one or the other, and A or B but not A and B. Okay, one or the other but not both. Equivalence, elimination, and introduction. Exclusive disjunction essentially means either one but not both nor none. In other words, the statement is true if and only if one is true and the other is false. Okay, maybe I should put this in here. Okay, and then add some information here. Wait. XOR exclusive OR, okay, or exclusive, okay, or essentially means either one but not both. But not both nor none. One or the other but not both. I prefer this informal way of saying XOR, I guess. Maybe using that one or the other but not both. Yeah, maybe something like that. Okay, I mean, I'm not sure why we need this yet. Exclusive or in natural language. Oh, interesting. Disjunction is often understood exclusively in natural language. In English, the disjunctive word or is often understood exclusively, particularly when used with the particle either. Oh, This example below would normally be understood in conversation as implying that Mary is not both a singer and a poet. Is not both a singer. Mary is a singer or a poet. However, this junction can also be understood exclusively, even in combination with either. Wait a minute. One or the other, but not both. Oh, okay. For instance, the first example below shows that either can be felicitously. In linguistics and philosophy of language, an utterance is felicitous if it is pragmatically well formed. An utterance can be I'm still not sure what this means. Let me check. Okay. Oh, okay. The first example below shows that either can be felicitously used in combination with an outright statement that both disjunct are true. The second example shows that for inclusively, even in combination with either. Oh, okay. Yeah, the first example, this one. Oh, below. Is this? Oh, maybe this one. Okay. The first example below, right? So that either can be felicitously used in combination with an outright statement that both disjunct are true. Okay, this one. Or both, right? The second example shows that the exclusive inference vanishes away under the downward entailing context. If this junction would understood as exclusive in this example, it would leave open the possibility that some people ate both rice and beans. Nobody ate either rice or beans. Were understood as an exclusive in this example, it would leave open the possibility that some people ate both rice and beans. Oh. Right. Example as the above have motivated analysis of the exclusivity inference as pragmatic conversational implication calculated on the basis of an inclusive semantic. Implicature are typically cancelable and do not arise in downward entailing context if their calculation depends on the maxim of quantity. Some researchers have treated exclusivity as a bona fide semantic entailment and proposed non-classical logic which would validate it. This behavior of English or is also found in other languages. However, many languages have distinctive constructions which are robustly exclusive, such as French. So I'm not sure how to pronounce this. Let me check. Oh, okay. Encyclopedia of Philosophy. Interesting. So we can see the exclusive or in natural language too. Alright. I didn't realize that. Yeah. Okay. Interesting. What is it called? Let's continue with the next question. And that is, let's save this for the last. How to read the Rex number from the page table. I found some possible what is it called? Possible answer. Let me copy this in the chat in case anyone wants to take a look at that. So let's take a look at this first. Is left or right shift depends on the order of how to read the beats. I'm not sure if we can call the endian here how to read the beat. Okay, let me read this first. Bit addressing. If the width of the register, frequently 32 or even 64, is larger than the number of bits, usually 8, of the smallest addressable unit, frequently called byte, the shift operation induces an addressing scheme from the byte to the bits. Okay, is larger than the number of bits, usually 8, of the smallest addressable unit, frequently called byte. The shift operation induces an addressing scheme from bytes to the bits. Induce an addressing scheme from bytes to the bits. Okay. Thereby the orientation left and right are taken from the standard writing of number in a place value notation, such that a left shift increase and a right shift decrease the value of the number. Okay, wait a minute. Let me open this. Positional notation, also known as place value notation, is the property of a numeral system that the value represented by its symbol in a written numeral depends not only on its appearance but also on its position. Its symbol fits in a specific place or position. Its symbol fits in a specific place or position, representing a power of a fixed space. The most common numeral system used today The Hindu-Arabic numeral system. Oh, the Hindu-Arabic numeral system is a base 10 or decimal positional number system. It is presently the most common decimal system. Oh, okay. Wait, that the value represented by its symbol is a written numeral depends not only on its appearance but also on its position. Its symbol fits in a specific place or position, representing a power of a fixed base. Is the number of unique digits, including the digit 0, used to represent number. For example, in decimal system, the radix is 10. Oh, the radix or base used to represent number. Okay. Is a positional system in base 10. Each of 10 numerical digits is a distinct symbol representing 1, the number 0 through 9, and in the context of the full numeral, its symbol's value is the digit multiplied by a power of 10. And in the context of the full numeral, its symbol value is the digit multiplied by a power of 10. Oh, I assume this full numeral means the full base, I guess. For example, what is it? This one is 0 through 9, right? And then when we hit the 10, the number 10, it's like we multiply by the power of 10. Something like that, maybe. And if it is in binary, it's like we multiply by the power of 2. Because binary is base 2, not 10, if I understand correctly. Most early numeral systems, such as Roman numeral, are essentially based on the additive principle. Its symbol type represents one fixed value, and the value of a numeral is the sum of the values of the spirit symbol. Okay, let's take a look at this. The binary numeral system base 2 is used in almost all computer and electronic devices because it is easier to implement efficiently in electronic circuit. Okay. History of positional fraction. So basically, it means the position of the number matter, maybe something like that. Let me check the big endian, or maybe endianness here. Is the order in which byte within a word data type. Okay. A word is a fixed size datum handled as the natural or historical unit of data by the instruction set or the hardware of a process. The number of bits or digits in a word is an important characteristic of any specific processor design or computer architecture. Okay, endianness is the order in which bytes within a word data type are transmitted over data communication medium or address in computer memory, counting only byte significance compared to earliness. Okay, endianness is primarily expressed as big endian or little endian. Okay, computers store information in various size group of binary bits. Each group is assigned a number called its address that the computer used to access the data. On most modern computers, the smallest data group with an address is 8-bit long and is called a byte. Larger group comprise 2 or more bytes. For example, a 32-bit word contains 4 bytes. Okay. There are two principal ways a computer could number the individual bytes in a larger group, starting at either end. There are two principal ways a computer could number the individual byte in a larger group, starting at either end. Okay, let me put this. Should I put that before the left shift explanation? Maybe this in this one. Okay. Reference. Let me copy this in the chat in case anyone wants to take a look too. Yes. Wait a minute. At least from this one, it looks like that is the case. If the left digit are read first, this makes up a big endian operator. Okay. Yes, it looks like the what left shift or right shift to depends on the order. Is it the order that the bit rate or okay, a big endian system stores the most significant bit in computing. Bit numbering is the convention used to identify the bit position in a binary number. The bits can be those in a memory byte or word, or those of an internal CPU register or data bus. Okay. Not how to read the bits. Most significant byte of a word at the smallest memory address and the least significant byte at the largest. Oh. Contrast store the least significant byte at the smallest address. Those closer to the digit of number are written left to right in English. Oh, the order of how the bits written, maybe something like that. How the bits written. Oh, maybe how the bits store. The point is the order here. And the order of the stored bits, the order of the stored bits of the of how the bits store information, maybe something like that. How the bits store information. The bits information, maybe something like that. This order of the bits information called endian, and there are two type of endian: big endian and little endian. Okay. The most significant byte of a word at the smallest memory address and the least significant byte at the largest. Okay. Big endian is thus closer to the way the digits of number are written left to right. Comparing digit to bytes and assuming address increase from left to right. Okay. How do I explain this? most significant byte. Let me check this. Bit significance and indexing. Wait a minute. Let me put this in here, and let me put this in the chat too. Hello, ping pong poing. Welcome, welcome. We are currently still on chapter 18, patching introduction, and trying out the homework simulation here. Basically trying to understand what this Python script do, like how to do the translation virtual to physical trace with linear page table, something like that. And currently learning about the endian here, the order of, what is it called, the order which bit that store information, maybe something like that, or maybe bit significance. That's what we are learning currently. Wow, good luck. Thank you. Okay, yeah, the least significant bit is the bit position in a binary integer representing the lowest order place of the integer. The lowest order place of the integer. Yeah, I'm kind of confused. Is it most significant bit or most significant byte? I mean, the address is 8-bit long and is called a byte, right? So if we call this byte, does that mean it is 8-bit long or something like that? But this one, it is called bit, most significant bit and least significant bit. Oh, most significant bit, least significant bit. Represent the highest order place of the binary integer. The least significant bit is sometimes referred to as the low order bit due to the convention in positional notation of writing less significant digit further to the right. The less significant bit also may be referred to as the rightmost bit. Okay. The most significant bit is similarly referred to as the high order bit or leftmost bit. Bit indexing correlates to the positional notation of the value in base 2. For this reason, bit index is not affected by how the value is stored on the device, such as the value byte order. Rather, it is property of the numeric value in binary itself. Wait, what? Bit indexing correlates to the positional notation of the value in base 2. For this reason, bit index is not affected by how the value is stored on the device, such as the value's byte order. Rather, it is a property of the numeric value in binary itself. This is often utilized in programming via bit shifting, correspond to the end bit of binary integer. Okay. The user may later recover this information by extracting the least significant bit. Okay. Let me try understanding this. At the smallest memory address, at the largest, big endian or most significant bit, less significant bit at the smallest, left to right. Okay. Left to right, right to left. Maybe something like this. Or more significant bit on the left. Least significant bit. Least significant bit on the right. And this one is the opposite. Wait a minute. Okay. Okay, something like this. Least significant bit on the left, most significant bit on the right. Let me highlight this. Okay. I assume something like that. And then okay. Which mean that how left shift or right shift behave depends on whether the system increase a byte address by 1. Okay. Disregarding the boundary effect. Okay, disregarding the boundary effect at both ends of the register. Arithmetic and logical shift operation. Arithmetic and logical shift operation behave the same, and a shift by 8-bit position transport the bit pattern by 1 byte position in the following way. I think what is the same is what is it called? It moved by a bit position, maybe something like that. Disregarding the boundary effect at both ends of the register, arithmetic and logical shift operation behave the same. Wait, is arithmetic also different? Okay, interesting. Let me check. Arithmetic bitwise operation, big endian and little endian. Yeah, let's add question mark because I'm not sure yet. Okay, let me check this. Or maybe this one. Okay, how to affect data storage and why it matters in computer architecture and network communication. Okay, wait, let me copy this in the chat in case anyone wants to take a look. Okay, CPRPNK said endian is about significant of byte. Big endian would be the most significant byte, appears at lower memory address. Left and right is confusing here. There are only low memory address and high memory address. So is big endian and what is it called? And least endian only in terms of byte, or maybe memory address? Is that it? Yeah, I'm trying to understand this one. Increase the or decrease the byte address. Byte address, okay. Yeah, I'm trying to understand what is the effect of the endian with left or right shift, something like that. Okay, maybe something like this. What is it again? Most significant byte. So is it byte or bit? That's what I'm still confused. I mean, sometimes it is called byte, sometimes it is called bit. So yeah, I'm not sure. Is endian work in memory address scope or in the bit scope? Most significant byte maybe. Big endian first byte appearing in memory is the biggest. Okay, let me try to understand this. The most significant byte. First byte appearing in memory is the biggest. So let's say we have, what is it called? Memory address, something like this, right? Yeah, maybe something like this. Is this the most significant byte? And this one is the contact is big endian. The significant byte. Is that it? Or maybe something different. If that's the case, significance of byte. Yeah, I'm still not sure about significant byte here. Is it byte or bit? I mean, some explanation said that 8-bit is usually called a byte, right? So that's what I'm confused. Is it byte or bit? In this case it is bit. So maybe the big endian or least endian, I guess, is the whole binary representation here rather than in bit. Byte significant. Okay, so it is in byte. So maybe, and what is most significant? The highest order place of the binary integer. So most significant byte is, well, according to CPR PNK here, bit at lower memory address. Is on lower memory address. Byte on the higher memory address. Maybe something like that. Now you have a choice in what order do you want to split. To be stored in memory. Now the question is that, is big endian and little endian have any effect on the left or right shift? Okay. On most significant byte on lower, or maybe using a pair on lower or higher memory address, and this one is lower memory address. Maybe something like this. On higher memory address. Now this is the question. No. So okay, so little endian and big endian ordering did not have any effect on the left shift or maybe right shift too. Okay. All right. Now if we do right shift or left shift with that, is it gonna be different? Yeah, I'm confused about this statement. A left shift by egg position increase the byte address by 1. Meanwhile, big endian ordering decrease the byte address by 1. That's what I am still not sure. So, is left or right shift behavior depends on the endian ordering here. Again, I'm not sure if this information correct or not. Something like that. And shift them manually. Okay, well, I have some example here. Think we can use this one. The address will change, but the number value will be the same when read out. Or yeah, well, we can use your example, I guess. Yeah, let's use this one. Okay, this is 8 by 8, right? And then if we do, what is it called? To left shift, something like this, right? This is the little endian, and this is the big endian. Okay. Yeah, left shift. This is also left shift. Wait, not that. Okay. The address is different, right? But how? Okay. Notice if you shift egg time, the one is in the next byte address. Shift egg time. Okay. Oh, this one is in the next byte address. Okay, wait, maybe something like this. Yeah, maybe. Okay, wait, hold on a minute. Okay. Maybe this is the spiration, and then shift this by egg time. Okay, maybe something like this. Oh wait, yeah, let's just do this. We're shifting this one. This is egg, right? Shifting egg time. So I assume something like this. And then, is this what you mean? If you're shifting by egg time, 1, 2, 3, 4, 5, 6. 7. Wait, can we like using this one? I'm kind of curious. No, okay. Okay. What? I forgot. Is this something like this? Oh, okay. Alright. We shifted 7 times. Now you need to press to represent the number. Wait, what? No, I need to byte to represent the number. Wait a minute. Is this something like this? Did I save? Did I save 7 times? Oh, okay. Yeah. There is some difference here. Okay. Right. Okay. Until 8, something like this maybe. But this one. Okay. Alright. Yeah. Shifted 8 times. Okay. Notice after to shift the one jumps to the next byte address. To shift the one jumps to the next byte address. Okay. Oh. Okay. So for example, let's say we have this and then let's save again. Okay. Bit shift will not change the integer value of the number stored no matter Indianness of the platform, but bits will shift around in different way. So the value does not change, but the shifting interpretation change. Is that it? Okay. Let's say we have this one and then this becoming. Yeah, I'm trying to understand. Coming something like this and then shifting again until is it? I think we copy this until 8. Okay. And then after 8, we need to, okay. It will, wait a minute, okay, this is 7. Alright, so this one jump to the next byte, I guess, rather than something like this, I assume. Okay, wait. So every time we shifting, we are moving, we might move the bit into another byte. Okay, if you shift one to on each platform, one by one position, you will get 2 on each platform. And I assume each platform in here means the endianness. Okay, so, okay, interesting. Wait a minute. So does that mean left shift or right shift, this does not depend on the order or endianness? I mean, if I remember correctly, my machine is little endian. I'm not sure if I have big endian here. Okay. If this is the case, right, then the big endian here would be something like this, maybe. And this one and this one. Wait, no. We're shifting this by, I guess so. Wait, is this the same? Is the shift happen on the CPU? The CPU will always make sure shifting left is on 1 is the same as multiplying by 2. Then when the CPU stores the number back out to memory, it will store the number appropriately. Okay. Now I think I kind of get it. So the operation is still the same, like regardless of the endian order, the left shift will still multiply by 2. But when we want to store the result in the memory, that's when the endian, what is it called? That's when the Indian matters. Something like that. Oh, okay. Yes. Let's so not like this. Let me try to explain this again. No, when we calculate when we calculate the result from left or right sieve, the order of how the bytes store Indianness, something like that, maybe. Wait, Indianness, okay. When we calculate the result from left or right sieve, what is it called? The value is still the same. Left sieve will multiply by 2. Right sieve will divide by 2, and then when we are trying to store the information, to store the data in the memory, that's where the ordering of the bytes come into the bytes or Indian must come into let's see if operation okay, and that's when we are trying to store the data in the memory. That's where the ordering so regardless of Indianness of the platform, the result of left or right sieve would be the same. Okay. The wiki is confusing here because it talks about how the address shift when the CPU store the number back to the memory. Yeah, that's what I'm confused, right? And this is why I assume that the Indianness have any effect on the result of left shift and right shift. Yeah, it is confusing here. And again, I'm still not sure whether this is correct or not, right? So that is something to keep in mind. Anyway, thank you for the information. Now I feel like I got a little better at understanding this. It is correct. Oh, okay. Okay. It is correct in terms of what is it called? In terms of when saving into memory, I guess. So it depends on the what is it called? The byte address, right? The endian here is related to the byte address. Okay. Wait, let me okay. Let me add another information there. The same. Indianness in here related to how to the order of memory address, maybe something like this. Address, and there are two types of endian, and then we got this one, big endian, most significant byte on lower memory address, least significant byte on higher memory address, and then the little endian, least significant byte on lower memory address. Okay, remove that. To the order. Wait a minute. Order of memory address, and there are two types of endian. Big endian and little endian. Okay, and in this case, let me add the example. For example, little endian. Okay, let me put this here. What is it? Wait, okay. And then this big endian here. Not that one. Okay. Is this correct? For big endian left shift. mean we're shifting by 8, right? I think adding something like this. Wait, is this 8? Okay. Adding that, pushing this. To endian. And I assume this is the wait, yeah, maybe something like this. When we're left shift by egg, we got this one, and maybe also something like this. I'm not sure if this is correct. Okay, let me check. We are shifting this by 1. Okay, this is 1, and then 2. And then 3. 4. 5. Okay, wait a minute. 1, 2, okay, 7, and then we are going into the next byte here. Oh, okay. Little Indian is not correct. Oh, first have to byte before shift and after shift. First have to byte before shift and after shift. To byte before shift and after shift. Okay. Oh. All right. Before shift and after shift. Oh, so the byte is still 2. Okay. So we are shifting this, and then this becomes something like this. Is that it? Oh. But is the big endian here correct? Or maybe this is also 2 byte here. Oh, okay. Alright, oh, interesting. Okay, so we are not adding the last one. Oh, interesting. And this one, oh, wait. So this is, wait. most significant bit on hiker memory address. So it's wait, not bit but byte, right? We operate on the byte here. I assume this is most significant byte, and this is also most significant byte, I guess. Hello Jonathan K. Bro, are you by chance from Malaysia? No, I'm not from Malaysia. I'm from Indonesia. Actual Indonesian. I'm from Indonesia. Is anyone curious? Okay. Oh. Wait. What did I want to do here? Alright, I want to check which one is the hiker memory address. Okay, so wait a minute. Let me try this. Not byte. Okay. Alright. 256. And then change that to this one. Wow, no. Interesting. Yeah, I'm trying to understand the most significant byte and the least significant byte here. Okay. Oh, okay. Oh, okay. Yeah, if I have some way to check the big endian, that would be nice. Oh, think about how that one would move after it's safe. Python will not show you endianness. Oh, okay. Endianness is just how it's stored in memory. Alright. But now I'm curious, is there any difference when using little endian or big endian here? In here is how the order of memory address. Like what is it called? Yeah, is there any reason, or maybe the benefit of using big endian rather than little endian, or vice versa? not sure if this is correct. Most significant byte. Yeah, let's remove that. I mean, what is it called? Is there any effect? Wait, let me. Is there any effect whether we use little endian or big endian? Something like this, maybe. Right, let me copy this in here. Okay. Yeah, this is what I'm curious. Maybe putting this in this one as the new question. We use little endian or big endian. Let me try checking that. The byte order used for storing multi-byte data in memory. Oh, wait. Let me put this in here too. Okay. Different systems use different format, which can cause compatibility issue when transferring data between processor. Oh. What is endianness? Usually this is property of a CPU, but you see it a lot in serialization. When you send byte across a network, for instance. Oh. Okay. Yeah. What is it called? What I'm kind of curious, like, why the CPU choose little endian to store the memory? Maybe something like that. Oh, the least significant byte is stored first. The lowest memory address. Okay. Is this like ascending as and descending kind of stuff? Lowest memory address. Yeah, I'm trying to make an analogy, I guess. Most significant byte on lower memory address. Most significant byte. So the biggest byte is stored first. Do you have a good view of memory? No, not yet. I mean, this is the first time I learned about memory, I guess, with this book. And yeah, there is no talking about Indianness or something like that, as far as I remember. So yeah, I'm still not sure about the memory, other than it is linear, I guess. The least significant byte is stored first. How bytes are arranged in memory when storing multi-byte data types. Oh, okay. In here is how the bytes are arranged in memory when storing the data, guys. Okay, like view memory as a big tab with square. Each square can store 1 byte. Okay, 8 bit. Each square has an address that goes from 0 to that number. Okay, like you could say on your system in your RAM, the byte at address 1223 is 1222. Wait. 1 byte is number from 0 to 1. One byte is a number from 0 to 255 or whatever number. Oh, okay. The byte at address 123, let's say, right? Okay, let me put that in here. The address is 123. Have the value. What is it? 122. Let's say something like this. Okay. And then from my understanding, wait, the least significant byte in here is that the okay, lowest memory address. Most significant byte. The least significant byte is stored first, meaning lower memory address contains smaller part of the number. Contains smaller part of the number. Let's store 32-bit hexadecimal number, okay, in Little Endian format. Oh, wait a minute. Oh, from this one, from this hexadecimal number, we can translate that to this, I guess. 1, okay, 2, 3 from this one. Is that it? Okay. Sometimes the one to deal with number bigger than 255, so you have to use more than one square to start that number. Okay. The CPU knows how to interpret a bunch of consecutive square as a single number, but the order of the byte has to be set in advance. Okay. Okay. But the order of the byte has to be set in advance. Alright, would be the same. Okay. Same because the CPU knows how to interpret the memory address, I guess, based on the endian of the platform. Interpret the memory address based on the endianness of the platform. Okay, so regardless of endianness of the platform, the result of left or right shift would be the same because the CPU knows how to interpret the memory address based on the endianness of the platform. Endian in here is how bytes are arranged in memory when storing the data. Okay, maybe something like that. Okay. Common Little Endian processor. Endian and Big Endian. Okay. Oh, this one. Advantage of Little Endian. Once the multi-byte number is loaded in the CPU for a computation, endianness is irrelevant. Oh, okay. So if I understand correctly, endianness matter when the CPU read the memory address or something like that, but after that endianness is relevant. Okay, that is correct. and write back out. Okay, so something like this. Indianness matter when the CPU read or write to the memory, maybe something like this. So only matter when read or write to the memory. Okay. The advantage of letter endian is your arithmetic operation as the least significant byte is stored first. Okay, less intuitive for human as number appear reverse, requires bad swapping. Okay, So endianness matter when CPU needs to read or write to the memory. Yeah, something like this. That is why shifting does not change. Right. Because the, what is it called? The value is still the same, right? And it's how we store the value in the memory that's need the endianness. Store or read, I mean, something like that. Okay, that is interesting. Yeah, previously I didn't know about this at all. That's why I'm kind of curious how all of this work. Okay, and in little endian format, this is the value. Oh, okay. Least significant byte is stored first. Something like this. Storing this in big endian format. Okay. Hexadecimal number this one. Wait a minute. Let me try converting this to decimal, I guess. Okay. Oh, wait a minute. I think. Okay. Not like that one. yeah, I'm kind of confused how we store this. Okay, it looks like this 78 is from this one, and then 56 is this one, 34 is this one. Okay, interesting. You know this all makes sense when you have to deal with this while programming. I would recommend C as a programming language that forces you to have a good mental model of memory. Alright, yeah. Currently I'm trying to learn about this first. I've tried C previously, but yeah, I'm still not familiar with C. So yeah, maybe next time I will do some programming session. I mean, there is also a homework that requires code, right? Something like this. But we are only using the memory API, something like this. Not really using the bitwise operation, I guess. So yeah. Okay, wait. Okay, we are storing this one in this order. Okay, so this is the value. Okay. Least significant byte is stored first. Is least significant byte always at the right or the last? Wait, no, not that one. Maybe. Yeah. Is the least significant byte? Start first. Okay. Key difference here. Okay. The advantage of big endian, more intuitive, usually used in network protocol. Okay. Memory storage and data representation. Endianness play a crucial role in how multi-byte data is organized. Okay. Multi-byte data. change in memory. Maybe something like this. Repeating in decimal the number. The least significant part is 0.23 because it represents the unit tens and 100. Oh, okay. A little endian decimal computer would store it like okay. Let's think that we have this number 839023 would be the least significant part is this one. Okay, this, alright, this is in decimal, I guess. Decimal, right? Significant part 0.23. Okay. Because it represents the unit tens and okay, 100. Okay, so in little endian memory case, little endian order, it would be something like this. And then in the big endian order, it would be something like this. Okay. Wait. Example of left shifting in big and little endian, and then least significant part. Significant part. Okay. Example of significant part. Okay, let's say we have number 1, 2, 3. Wait. Okay, 9023. Split that in. Split that to. Okay. Something like this. Okay. significant part is we have decimal number to make it easier to understand. It is in the 100, I guess. Oh, hello, Matt X. While live stream, it's better to study in peace. Well, so I can discuss with someone else, For example, the CPRPNK here, what is it called? Explaining to me about how Indian work, Indianness, something like that. And if I just looking at the Wikipedia here, I might have misunderstood what the Indian ordering here means, So that is one of the reason I'm doing the live stream. In case what my understanding is wrong, someone can correct me, or we can discuss something like that. I mean, that is the, what is it called? That is the disadvantage of learning by ourselves, is that we what is it called? It is kind of hard to validate the information that we got, So it's nice to be able to discuss with someone else, especially if that person have more information that the information that we have, something like that. So yeah, that's why I'm doing live streaming, in case anyone want to have a discussion or something like that. Okay, wait a minute. It is in the hundreds. Yeah, how do I explain this? Because, let me check. Least significant part in decimal number. Okay, significant figure. Oh, okay. Is this what it means by least or most significant? Let me copy this in the chat in case anyone wants to take a look. Also refer to as significant digit. Okay, a specific digit within a number that is written in positional notation that carry both reliability and necessity in conveying a particular quantity. When presenting the outcome of a measurement, such as length, pressure, volume, or mass, if the number of digits exceed what the measurement instrument can resolve, only the digits that are determined by the resolution are dependable and therefore considered significant. check. Rules to identify significant figures. In a number requires knowing which digits are meaningful. Which requires knowing the resolution with which the number is measured, obtained, or processed. If the measurement mass is this one, okay, and the measurement given as this one, the 4 is not useful and should be discarded, while the 3 is useful and should often be retained. Related but confusing. The significant digit is the smallest, most significant is the biggest. Okay. Trailing zero in an integer may or may not be significant. Okay. 3, 4, or 5 significant figure depending on how the last zeros are used. For example, if the length of a road is reported as this one, without information about the reporting or measurement resolution, then it is not clear if the road length is precisely measured as this one or if it is a rough estimate. Okay. Disregard everything is just read. This is just in the context of scientific measurement. Okay. Is that different? Let's try this one. Lowest exponent value in the rightmost position. And the most significant part is maybe something like this. Okay, let me copy this in the chat in case anyone wants to take a look. Okay. In the rightmost position, for example, in the number 2516, the 6 is the least significant digit. The exponent value refers to the power of the base number that is multiplied by each digit. Base 10, 2516 represent this one, or 2510 and then 6. Okay. 0 is the lowest exponent of 10 in this representation, therefore 6 is the least significant digit. Okay. I feel like this example might be easier to understand. Let's say we have decimal number 2516, which represent power 3. Let me add this one, I guess. Okay. 10 power 2. Okay. Power 1. So 6. 10 power 0. Or 2000 plus 500 plus 10 plus 6. Okay, 0 is the lowest exponent of 10 in this presentation, therefore 6 is the least significant digit. Okay. The least significant part is, I guess, 6. In this case, because 0 is the lowest exponent. The lowest exponent in this representation. In this decimal, something like, you can do the same with binary. It's just power of 2 instead of 10. Alright, okay. Okay, yeah. We are currently trying to understand in the decimal format to make things easier, I guess, because 0 is the lowest exponent in this decimal representation, and I assume the most significant is 2000 here, maybe something like that. This is the least significant digit. Okay. But notice NDNS is about the significant byte and not bit. So we are talking about significant digit, but so we are okay. So we are alright. So we are not talking about significant digit, but the grouping of the digit. Okay. Alright. Yeah, I just realized that. Okay, split that to because we are talking about understand because Indianness is about the grouping of the digit, not the digit itself. Correct me if I'm wrong. Indianness, okay. To understand because Indianness is about grouping of the digit, not the digit itself. Okay. The least significant part is this one. And in decimal we arbitrarily group by 3 and in binary by 8 for no good reason. Yeah, I am still not sure why we are grouping like this in decimal number, but it is what it is. There's a lot of mystery in here. Okay, the most significant part is this one. Okay, let's put it like this. Alright. We can also do this in byte. Okay. Alright. Okay. Maybe we will try answering this question on the next session, I guess. Let me put this in here. Like, I'm kind of curious if there is any effect whether we use little endian or big endian, something like that. I mean, from this article it looks like it is simple arithmetic operation. The least significant part comes first. Okay, wait. Yeah, let's try exploring this on the next session. Thank you to CPN PNK for the information. Otherwise, I will misunderstood about endian. Okay, so that's it for now. Thank you for watching and see you next time. Bye bye.